Let us talk about the properties of before that. Let us talk about the properties of full binary trees that are listed in the slides, and we'll prove some of these properties. So in full binary trees, what we're going to do is we're going to assume n is the number of nodes, L is the number of leaves, and I is the number of internal nodes. Okay, in a binary tree, in a full binary tree. And what are the properties that we have? We have this property which says A, L equal to I plus 1, B, N equal to 2I plus 1. Then we have I is equal to, which is obvious from this, N minus 1 from B, for example. L is equal to N plus 1 over 2. Have N is also equal to 2L minus 1, follows from B. And have I equal to L minus 1, which is obvious from A, and so on. So what this actually tells us is that if we know N and we know that it's a full binary tree, we can find N, I, or L, any one of them, they are interrelated. Okay, this is what it's telling us. Okay, and so let's try and prove one of these properties. Let's take A. If T has I internal nodes, then the number of leaves L is equal to I plus 1. Let's see how we prove this. We'll prove this using induction. And we'll do induction on I, which is the number of internal nodes. Okay. Let S be the set of all integers I greater than or equal to 0 such that T is a full binary tree. Okay, such that T is a full binary tree. Okay, then with I internal nodes. Then T has I plus 1 leaf nodes. Okay, of the base case. I equal to 0, L equal to I plus 1. Since it's a non-empty binary tree, since root is the only node, it has no children. Okay, it has no children, therefore a leaf, therefore it is a leaf, and also full binary tree. Okay. Implies one leaf node. That means what? 0 belongs to S. Okay. What's the hypothesis? We're going to look at, assume that this is true for some k greater than or equal to 0, every I from 0 through k is also a k is a full binary tree that is in S. What is S now? S is the set of full binary trees which satisfy this property such that L equal to I plus 1. Okay. Now, the proof of this is, assume, let T be a full binary tree with k, we'll add one internal node, okay, k plus 1 internal nodes. Okay. So when it was 0, it was only the root. You don't have an empty binary tree. Suppose L and R are the left and right subtrees. Respectively. Okay. Let IL and IR be the internal nodes in L and R. So clearly, the every internal node in IL and IR are internal nodes of tree. Okay. So we said we're adding 1, right? So k plus 1 is equal to IL plus IR plus 1, because now neither left subtree or right subtree is empty, and we have plus 1 because 1 is due to the root. Is an additional internal node. Okay. So clearly, by the hypothesis, by the induction hypothesis, we know that it is true for every k, 0 through k, L must have IL plus 1 leaves. Similarly, R must have IR plus 1 leaves. Every leaf in L and R are the leaves of T. Right? No problem about this. So what do we have? The total number of leaves is IL plus IR plus 2. Why is this true? Because the induction hypothesis, we are looking at, for example, if you remove the root node, for example, it is k, at most k. Okay, some k. All right. From here we have, from this equation, we have IL plus IR equal to k. Okay. So T has k plus 2 leaves. Where do we get this? We get this from here. And these two terms. Okay. Where does this come from? Because k is k plus 1. The one internal node is the root. Okay. And it's true for k. Up to k we have said. Okay. Therefore, T has k plus 2 leaves, or k plus 1 belongs to S. S belongs to 0, infinity. Okay, that means all positive integers in terms of number of internal nodes belong to the binary tree. Now let's do one more theorem. There are many, each one of them you can prove. This is with, I've done only with full binary trees there. Let me take a general binary tree, which is full and complete and balanced and all that. Or it's also called a perfect binary tree with lambda levels. I'll tell you what a level is. Then the number of levels is at most 2 to the lambda minus 1. Root is at level 1 and level 2 and so on. What is the meaning? This is the maximum, then the number of leaves, this is leaves here, is at most 2 to the lambda minus 1. This is level 3. See, this is 2 to the power 2 minus 1. So level 2, 2 to the power 2, 2 to the, 2 to level 1, 2 to the power of 0, 1, 2 to the power of 2, 2 minus 1, I'm sorry, 2 to the 2 minus 1, 1, therefore 2 nodes, and level 3 has 4 nodes and so on. So it's easy to verify this. Let's prove this. And here again, we will assume that it is true for all lambdas. Let S be a set of integers lambda greater than or equal to 1, such that if T is a binary tree, with lambda levels. Then T has at most 2 to be lambda minus 1 leaf nodes. Is what we want to prove. Okay. We'll again use induction. The base case, if lambda equal to 1, then the tree has only one the root. The root no children. One leaf node equal to 2 to the lambda minus 1. Level is 1, that is equal to 1. 1 belongs to S. Okay. Let T be a tree with, okay, I forgot to give the hypothesis. Hypothesis, just like before, we will assume for some integer k greater than or equal to 1, all the integers, just like we assumed all of them are in S, integers 1 through k are in S. That is, when a binary tree has m levels, m less than or equal to k, it has at most 2 to the m minus 1 leaf nodes. Now the proof, let T be a binary tree with k plus 1 levels. So we're looking at a tree T with maximum number of leaves. Okay. T has so two non-empty subtrees S1 and S2. Let S1 and S2 have M1 and M2 levels respectively. And clearly that's less than or equal to K. So if M1 and M2 are between 1 and K, implies number of leaves nodes, maximum number of leaf nodes in S1 and S2 is 2k plus 1 in S1, 2k minus 1 in S1, and 2k minus 1 in S2. total number of nodes, leaf nodes is therefore 2 into 2k minus 1. And this is nothing but 2 to the power of k. Why does this happen? Because we're looking at the roots to subtrace. This one is having n1 levels, this is having n2 levels. This is a k plus 1 level tree. And what is the maximum number of nodes? By the induction hypothesis, it can have 2 to the k minus 1 nodes. And we add both subtrees to get the total number of nodes and total number of leaf nodes. And this is 2 to the power of k. Therefore, applying the induction hypothesis, we have k plus 1 belongs to S. Therefore, when you're looking at S over here, like 1, all positive integers. So the depth or the level of the tree is between 1 and infinity. Okay.